We're going to start this section today. We're going to only get through part of it. Focus. We're only going to get through part of it. Then next week, we're going to continue a little bit of it. We're going to do a lab on this topic. We're going to then continue to finish making the catapults. We're going to test the catapults. And then we're going to do a catapult analysis. So we have 3 full periods of catapults still to do. Okay, one of them will be the second period of a double. One of them will be testing in the gym. And the third day we will be up here and we'll do some math that is involved with the catapults.
This is all next week?
It's all next week pretty much. So next week will be a more relaxed week.
One period to finish the actual structure?
There's going to be 1 period more to finish the structure of the catapult. I think you'll be able to.
I don't know. Because
If not, I'll figure it out. Don't worry. We'll figure it out. I did get new glue. So let's hope it works. The other class with the new glue really went pretty quickly through it. So, who used the Gorilla Glue last time? Who ended up using it? It came out pretty good.
It works for ours.
Yeah, I looked at a few of them. The ones that seemed to use it came out pretty good. But it just takes time to set. That's why that's a little tougher. Anyway, we'll figure it out next week. Let's get to what we're doing today. So, the topic of circular motion, okay? So far we've studied either 2 things. We've studied linear motion, with objects moving either left to right or up and down. We've also studied linear momentum. And then we've studied projectile motion, which is 2-dimensional motion. But that involves a parabolic flow, not a circular flow or circular path. So we're going to specifically look at things that move in some sort of a circular manner. Why do you think this is its own topic in physics?
Because it has to do with like pi and circles.
Guys, don't just start talking when others are answering.
That like horizontal like straight lines don't do it, so it's like its own
Yeah, it's its own subtopic, okay? It's still motion, but it's a specific type of motion. And it's a motion that is actually much more apparent or much more frequent than most other types of motion. Think about like anything you do from the morning to the end of the day. At some point in the day, there's something that you are either involved with or something that you're associated with that moves in a circular fashion. And I guarantee you can figure out every day of your life, there's something that's moving with some circular motion. Whether it be taking the train to school, okay, whether it be taking a bus to school or getting a ride, the wheels, those move in a circular pattern. Or maybe it's at home, you microwave something. The microwave plate, what does it do? It moves in some sort of a circular motion. What if you go home and you put the washer on, the dryer? What does the tub with the clothes work? In a circular motion. The toilet bowl, you flush the toilet bowl. It moves in a circular motion. Absolutely. Everything has some sort of circular association with it. These 3D printers, the gears that feed the actual filament through, move in a circular motion. So there is so much, what's the word? Not frequency, but circular motion occurs in everyday life a lot. Almost more, I'd say, than actually things that are moving linearly. The invention of things moving circular was a huge deal. And you guys study history and you study ancient civilizations, but the invention of the wheel was huge. Think about it. Imagine if you didn't have wheels today and nobody thought of using a wheel with an axle. How would cars move? They'd have to be pushed. They'd have to be pulled by a horse and buggy pulling a flat surface. There'd be a ton of UK. A lot of friction, right? The coefficient of friction on a street between that and a wooden platform is very high, as opposed to a wheel that's moving, okay, a wheel that's propelling forward. So the idea of circular motion is extremely important, right? The 2 major objectives we're going to look at are tangential speed and centripetal acceleration. And then we're going to understand what are called the causes of circular motion, what has a tendency to give circular motion. So let me quickly start with something very simple, all right? So we've talked about the word pendulum before, so anything on the end of a rope or a string or a rod is a pendulum. Now, what did we call this at the end again? What was the term for it? I gave the name real quick. It's a person's name, it's a man's name. This is called the bob. Very good. Good memory. Okay? The bob. Well, grandfather's clock has a pendulum which has a bob. Anyway, anything that's swinging back and forth at the end of something is called a bob. This is some sort of circular motion. So, and then you spin it like this, now it's a circular motion, right? Now, what's keeping this object from just flying off? What's keeping it from like flying at you guys and swinging this way?
Your hand.
The what? The string, okay, good. The string, what about the string though? What about it?
Pulling it
It's pulling it back. It's pulling it back. So what do you call that when a string is pulling on something? It's what? The string's what? Force. What kind of force? Very good. We'll talk about centripetal force in a minute, but it's a little more specific. But what is the force? When I take a string and I go like this, what's keeping me from ripping the string apart? The what? The tension. Good. The tension. So the string's tension force is what's keeping this object moving in a circular fashion. Now, if I wanted to, say, throw this object into the wall there, when should I release? When it's like here? Or is it like here? Specifically.
the top.
At the top? Did that work?
A little bit.
Fail.
A little bit? Okay. Let's try a little.
The bottom.
Alright. So if I want to go this way. If I stop, ready? If I let go when it's on the right side, it just goes right to the ground. Sorry. It's only rubber. Throw it back. It's over here. So, if I were to let it go at the bottom, though, obviously, I'm sorry, it's going to launch this way, okay? Now, if I threw it to the ceiling, I want to let go on the left-hand side. So what you're noticing is, depending upon where the object is, its velocity goes in a certain direction. Its trajectory will move in a certain fashion. Now, the term tangential speed is what I'm really referring to right now. Guys, focus. The term tangential speed is what I'm referring to. So, the tangential speed obviously is the speed of the object in the end. What does tangent mean from math? Last year, you may or may not have learned the term tangent. Has anyone heard the term tangent from math before?
It's opposite over adjacent.
Ah, good. Okay. Not trigonometry though, with circles. That is true. Opposite over adjacent. Very good. What's tangent with circles, not triangles, with circles? You know what circles got?
It's also when there's isn't it when there's a line that's hitting the outer edge of a circle, and then the tangent is that
That is exactly what you said. It's the line. It's the line hitting the opposite or on the outside of the circle. So if you draw a circle, whoops. If you draw a circle, a tangent line looks like this. It's a line that intersects the circle at one given point. That's a tangent line. Another line that looks like this is called a. That's an S. A secant. Secant. Okay? So when we're talking about tangential speed, okay, when we're talking about tangential speed, we're talking about the speed of the object on the outer edge of the circle. So if you pause, okay, as I'm spinning this, if I paused it right here, and I let go, a minute ago we said it's going to shoot up to the ceiling. When I let go at the top, it went over that way. When I let go on the side, it hit the ground and then bounced out towards you guys. But what you're noticing is that depending on where I let it go, the object moves in a different location or a different orientation. So what we're going to see here is when we define this, the tangential speed, is the speed of an object that is tangent to the path. So when I was spinning this a minute ago, which way was I spinning it? So you guys could see it. I was spinning it this way. Okay, so let's draw a circle this way with arrows. So I want to draw this, this way. All right, so draw your arrows like this, please, to show that it's moving counterclockwise. Which, by the way, in case those of you have never understood clockwise and counterclockwise, a simple way to do it, think about which way the hands move on a clock. They move this way, so that's clockwise. It's like a clock. Counter means opposite of a clock. So this is counterclockwise motion. All right, so right now I'm currently spinning it like this. Or if I turn around, I'm going to do it this way so it's easier. Okay, I'm spinning it like this. All right, does that make sense? The way I'm spinning in the arrows on the page? You need to be able to make that connection. So if I let go at the bottom, we said it's going to shoot that way. So that means that right here at the very bottom, if you drew a tangent, wouldn't the tangent look like this? And that tangent is indicative of the location or the direction it will move. So draw yourself a tangent on the bottom real quick. Okay? So make believe this is a rubber stopper. make believe the rubber stopper is at the bottom right now. Okay, there's the rubber stopper. Draw yourself a tangent line, and then look at the arrows. The arrows in this diagram tell me that when it's at the bottom, the arrow points this way, right? And this side, the arrow points up, and the arrow points left at the top, and then on the left side, the arrow points down. So since the arrow is pointing this way, and since I'm spinning it this way, I can put an arrow at the end of my tangent line, and this is what indicates the direction the object will move if it's released there. Now, it's really a ray. I could erase this like that, and just draw a tangent ray instead of a tangent line. Remember, a ray has an endpoint. It only extends infinitely in one direction. A line extends both ways. So when I let go of the bottom, it goes in that direction. So depending upon where it's let go, the object, where it's released, it will move tangent to the path that it was on. And it will move in the direction of the actual motion. So if you pick any point in time along this path, okay, so pick a spot along the path, the right-hand side over here. Oops. The right-hand side right over here. Okay, imagine it's over there on the right. Well, if I draw a tangent line and I see that the arrow on the right is pointing up, it's going to look like that if I release it that way. And what that was this. This was when, if I let go, it goes up to the ceiling and comes back down. Okay, so it's literally just letting go on this side, and as soon as I let go, it's going to launch up. That's that arrow that's showing. So you can draw an infinite amount of tangent lines. Pick a random spot. Pick maybe right here. Well, the object would go like this now. If I pick right here, the object would go like this. If I keep drawing tangent lines, I'm going to see that I can see the actual general path of this is counterclockwise. You kind of see how all these arrows point like this? They all seem to follow the flow of the direction I was swirling this in. Okay, so at any point in time, an object wants to move away from the circle. That's why when I let go, it moves away from the circle. But as several of us noticed before, the force of tension in this rope is what's keeping it from being launched away. There's tension in the rope that's holding it, that's keeping it on this path the entire time. Okay? All right, let's look at an example of this. Let's look at an example of this real quick. Here, imagine 3 people, all right, are at an amusement park and riding on a merry-go-round. So think about like a merry-go-round. So a merry-go-round, here's the center of a merry-go-round. Here's like a horse. Here's another horse. Here's a third horse we're going to look at. Here's the platform of the merry-go-round. That's not a good circle at all. Hold on. I should draw the circle first, right? To make it easier. So there's the center. And we have 3 horses. There's a bunch of other horses, obviously, on the merry-go-round all over the place. Okay? But we're specifically... This one's ugly. We're specifically looking at the 3 that are in line there. Now, in this problem, it says that 3 people are sitting on 3 different horses at distances r, 2r, and 3r from the center. All right, so this distance here is r. This next distance is 2r. And this last distance all the way out here is 3r. Okay? So they're just further away from the center. That's all it is. Now, if the floor of the merry-go-round is fixed, a fixed floor means like the horses are going to move in tandem. So if I were to, be the person on this merry-go-round and I'm on the inner horse, okay, here's the inner horse, here's the next horse, here's the third horse. They're going to move like this around the circle. They're going to move in tandem. Okay, they're moving together. This one's not moving faster. They're not moving at different velocities. So if the floor is fixed, then which person has the highest tangential speed? Okay, tangential speed. And if you recall what I said a moment ago, the tangential speed is the speed of the object as it moves along that curved path. So if we go through this and think for a second, this object is moving this way at this point in time. They're all moving straight up, really. Okay, then when they get up to the top up here, they all want to move this way. Okay, that's the way that they're all moving, and etc., etc. Now, how do I measure the speed of an object? What's the definition of speed for an object?
Acceleration of time. No.
Not acceleration over time.
Distance.
Okay?
I was listening
Yeah, distance. Oh, that's right. Distance over time. Distance over time. Now, if they're moving together, then that means that all three horses take the same time to complete one cycle, right? Because they're moving in tandem. So you're literally seeing all three horses do this, run the whole way, come back around to the beginning. Which of those horses travels the longest distance? It's a little obvious.
The one that's 3R.
Yeah, the one that's furthest away. What's the distance that you travel around a circle called? Circumference. So in reality, we could just think about this, that the one that's furthest away has a larger circumference. By the way, with circular motion, you're going to see a lot of stuff with circumference. So get familiar with the formula. Now, if I wanted to know what the speed of the first horse was, speed, remember, is again distance over time. So the first horse, what's the formula for circumference?
Isn't 2 pi r?
It is 2 pi r, very good. 2 pi, and I'm going to call this r right here, over time. That's the first horse on the inner track. Right? Here's horse 1 right here. Here's horse 2. Here's horse 3. How about the second horse? It's still distance over time for speed, but what would it be now? Wouldn't it be 2 pi r? What's the radius, or how far is the second horse from the center of the circle? How far is that second horse from the center of the circle? Kira? 2 pi 2r over time. And then last but not least, the third horse. How far away is that, everybody? Yeah, 3r, and 2 pi 3r is going to be the distance traveled. So, without even going into any math, it's obvious in this problem, it's obvious that the third horse will have the highest tangential speed. Okay, the highest tangential speed. Because look at the formulas. This one, right, the second one is double the first one. The third one is triple the first one. So this has got to be the largest speed. Remember, as you increase the numerator, the overall value increases. These are directly related. Keep using those terms. Okay, no direct relationships. Understand that. So, in your lab next week, you're going to have to figure out what the speed is of an object that you're going to be spinning things over your head, and things are going to be moving and stuff. You're going to have to figure out what the speed is of this. What's a good way to figure out the speed of this object? Because it's hard to measure the time for one lap, right? Ready, stop, go. Stop, go. Or go, stop. Go. Like, how are you going to time this? So what would you do?
Measure the radius, also the length of the string from your finger to the end, and then use a formula.
Alright, so that's the radius. Agreed.
And then maybe do instead of backwards.
How are you going to find the time, though, if you want to get the speed? So you can measure the radius for sure, right? Here's the radius. How are you going to measure time in a problem like this? What might be something you might want to do? Because the time for one loop is so quick that you're not going to be able to react fast enough. So what should you really do?
Find the time for a certain set and then divide.
Yeah, so how many maybe? Give me a number.
So 4.
Alright, so after 4 loops, find the time. And then divide by 4 to get the time it takes for one loop. So when you do this lab next week, I want you to think about that. Maybe count. So if me and Ed were partners, I'd say, ready, Ed, start counting. Count to 10. Ready, go.
1, 2, 3, 4, 5, 6.
Take it a little slow.
9.
Are you counting time or are you counting loops?
Oh! I was
Count
counting-
loops. Count
Oh,
loops.
sorry.
Okay, ready, go.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
It's a little fast. The idea
A
is
little
that
fast. No, it wasn't.
I think it was a little
You
fast.
started, you started
Slow.
before.
Alright, someone else now.
Well,
I
yeah, you
want
get
to
the
hear
idea.
someone else's.
So if you're spinning it this way, okay, ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But the idea is you count maybe like 10 laps or 10 loops, and then just divide your answer by 10. That'll give you the time for one loop or one cycle. And then you can put that in here, the time. So once you know the time, you know the radius, you can figure out the tangential speed for any object moving in circular motion. Now, for the sake of this section, what we're going to do is we're going to start looking at forces also. We're going to say, well, what is the force in the rope that's keeping it in motion? How much tension is there? And we can figure that out numerically. Jake, focus. You can figure this out numerically in these problems, okay? So let's look at an example now. Well, before I look at an example, let's take a look at a formula that we can use to look at an example. Okay? So, objects in circular motion objects in circular motion follow a certain trend that will be useful in our formula in a minute. Now, when this object is out here, it wants to move away. Think about, have you ever heard the term centrifuge? Centrifuge? What's a centrifuge? Anybody know?
It's like a thing that you put something and it spins it and you're supposed to set, it's like, it separates it.
Yeah, usually what thing you put in there? At a doctor's office, what do they use in a centrifuge? Anyone know?
What?
Yeah, they use blood. You gonna say blood too?
What, yeah.
They use blood. What do they do it for? They use it to separate your blood into what? Yeah, the different parts, the plasma, the red cells, the white cells, they all separate into different because they're different densities when it spins fast enough. Because things that are spinning want to move away from the center. They want to move away.
It's like that machine that just goes like around and around with all the tubes in it.
Yes, that's exactly right. Yep. And it separates it completely. The tubes are usually facing this way, so they separate by density. Now, the idea here is that this bob, or whatever, this rubber cork right here, is not moving away though. It wants to move away from the center, but something is keeping it from moving away from the center. So think about Newton's laws. For every action, there's an equal and opposite reaction. So if this wants to move away, which way is the rope pulling it? Back this way. If this wants to move up, really, it's pulling it. If it wants to move that way, it's pulling it. But what you notice is no matter which way it's always pulling toward the opposite or center. Good. Opposite of the way it wants to go, which is the center of the circle. So really, when I spin something, the force in the rope is literally pulling it toward the center. So the force of the rope is changing its direction. When the object is out here, the force is that way. When the object is up here, the force is down. When the object is here, the force is that way. So the force is literally always the radius, but inward toward the circle. So if you drew an object moving in circular motion, if you freeze frame at any point in time, the force that's being applied to it to keep it in circular motion is wherever the object is, say right here, and toward the center of the circle. So the force right now is acting that way, okay, when it was like this. So what we do is we use a term, we call that term centripetal, not centrifugal. Because a centrifuge wants things to move out, it separates things by moving out, and that's centrifugal at the end. I put that in parentheses not to be confused with. This is centripetal, which means center seeking. Centripetal is center fleeing. It wants to move away from the center. So the centripetal acceleration is the acceleration of an object that's directed toward the center. Why is there acceleration directed toward the center? Which of Newton's laws involves acceleration?
The second one,
It says,
in order to achieve the acceleration you want, you must apply a certain amount of force to the mass.
yeah, so it's the force and the mass that are involved in it. So if there's, again, as I'm spinning this, it wants to go away from the circle, so the force is pulling it toward the center. So if there's a force pulling toward the center, and Newton's law tells us F equals ma, if there's a force, there's got to be an acceleration. Unless that force is balanced. In this case, it's not. Okay, the force is only acting toward the center. So there's some sort of center-seeking acceleration. And that acceleration is not delta v over t anymore. Remember, linear acceleration was the change in velocity over the time period. It was delta v over t. The acceleration here is vt squared. What do you think vt stands for? Any idea? Take a guess. What kind of speed were we looking at a minute ago? Yeah, tangential. So vt is the tangential velocity. Jot that down, please. vt is the tangential velocity. All right, tangential velocity. Vt squared over r. And conveniently, this is indeed the right unit, or these are the right units. Take a look. Velocity squared over radius. Those are the units if I look at this problem, right? Units of velocity are meters per second. I square that because it's Vt squared over r. What's r again? Radius. So it turns out this becomes m squared over s squared all over m. One of the m's cancel with this squared term, giving me meters per second squared. So the units are correct because if you recall, acceleration as units of meters per second squared. So remember how I talked about simulating g-forces? I alluded to something called g-forces, what astronauts feel when they're in a rocket ship.
Is that like on
The
a
amount of
roller
gravity?
coaster when you go down?
Yes. Roller coasters are rated by the amount of g-forces that you exhibit on your body. So how could you increase the g-forces if you increase the numerator, which is the velocity? So I spin it faster and faster and faster. What's happening is I'm increasing the amount of force on the actual tension, which is increasing the acceleration on this body. If the acceleration becomes greater than 9.81, now you're traveling at more than 1 g. If the acceleration is 19.62, it's 2 g's, double 9.81. If it's 29.43, if that's the acceleration, it's 3 g's. So depending on how fast the acceleration, or how much the acceleration is, you can determine how many times faster it is than the Earth's gravitational pull. Well, that's how you simulate 3, 4 g's that the astronauts experience. They put them, and if you've seen them at Armageddon, they put them in this little machine and it spins them in circles. What it's doing is it's simulating g-forces on a person's body. Jake, are you paying attention?
Yeah.
Are you?
Yeah.
Please, focus. Look up, okay? Make sure you're focusing. So, in these problems here, we need to know how fast the object is moving, vt, and what the radius is. The radius is indirectly related. You see that? The radius is indirectly. And it means if I make the radius smaller, there's not as much acceleration. If I make the radius bigger and keep the same speed I just had, there's more acceleration. Okay, so as the radius increases, the acceleration decreases because it's in the denominator there. Now, let's look at an example of this before we do another application. So example 2 says a car moves around a circular track at a constant speed. If the radius of the track is 20 meters and the centripetal acceleration is 6 meters per second squared, then what is the actual speed of the car? So this car is traveling on the track, able to determine the actual acceleration that it's feeling. You know the radius of the track is about 20 meters or a little more than 60 feet. So figure out how fast the car is moving. What is the car's speed? So use that formula from the last slide. Start by writing the formula. AC equals VT squared over R. AC equals VT squared over R. Solve for V, or VT. Solve for VT.
So the VT is like one thing. Yeah, just one whole thing.
One whole thing?
Like it's not like V and
Oh yeah, it's a subscript,
Well,
correct. Yep. So for solving this, okay, T is the little subscript on the bottom there, so we're trying to solve for VT.
I need that. I need that.
The algebraic solution should be pretty straightforward for this kind of a problem. Multiply by R to get VT squared by itself, and then take the square root. What do you get? Check your work, please. I agree. Now, follow-up question. Follow-up question, 10.9. Yes.
Oh,
The C is a subscript and the T is a subscript. C representing centripetal acceleration, and T representing tangential velocity. If there's acceleration, there's got to be force. And that's what Alessia told us a minute ago with F equals ma. So if this is true, then the acceleration is given here. okay, we have acceleration or formula for it, we could also figure out what the formula is for the force that a body feels as it's moving around the circle. So think about this. If you have F equals ma, and you want to find the centripetal force, you can use the centripetal acceleration. Remember, F equals ma, Newton's law, always comes up. So we're going to use AC instead of A because we're looking for FC, the centripetal force felt. The amount of force felt on this object or this body. So as a result, what can we do? Okay, we can go ahead and take the formula for AC and plug it in right there, which was VT squared over R, giving us this formula right here. So again, FC is really M times A, but A is VT squared over R. The M could go on the top or out front. It's the same effect on the problem. But the idea here that we can see is that just like the acceleration was related to the velocity directly and indirectly to the radius, the same goes for the force. But the force that an object feels is also a function of its mass. So a bigger object on the end of here, right? Think about a heavier object. Wouldn't the rope have to pull harder? Imagine me spinning an object that was like a 2-pound weight. Wouldn't the rope pull a lot to keep that 2-pound weight in motion? So if you increase the mass of the object, you increase the force that the rope provides. Now I keep saying the rope. This is one example of an object in circular motion. Let's look at several examples now and go through this. Now, one thing I want to mention, this is not given on your formula sheet, this formula right here. But you are given the other one we had a minute ago, AC equals VT squared over R. You can always get this formula just by putting it together with F equals ma. So again, I'll write in red. You're given this on your formula sheet. This is given on the formula sheet. If you need to find the centripetal force acting on an object, just take this and plug it in for A, and you get this as a result. Okay, there's no need for me to give it to you because both F equals ma and AC equals VT squared over R are both on the formula sheet. Put them together, you get this bottom formula down here. All right? So let's look at it, some examples. What provides centripetal force? So before I get into what provides, we look at the examples. Centripetal force is a theoretical concept. Like a minute ago, what did you say provided the force keeping this in motion? What was it? The tension in the rope. So the first one there, an object swung around on a rope, like we're doing now, a tetherball. Like tetherball, have you seen tetherball before? Okay, tetherball from like Napoleon Dynamite, have you seen the movie? It's the force of tension in the rope. So for the first one, let's jot that down. The force of tension. What about a car that's going around a circular track? What keeps it from sliding off the track?
Well, I think we consider the wheel or the friction.
Friction. Very good. The force of friction. I'm not going to write force every time. Now, there's one other thing for a car, and this is a little bit more complicated to think about. Have you ever gone to any sort of a racetrack or seen like a NASCAR race on the TV or something? Ever look at the actual roadway? Anybody notice anything about it? What is it?
It's curved.
It's curved, but what's the other
It's
word?
like
Yeah, banked. We'll call that banked.
yes.
The turns are banked. They're banked turns. The reason for banked turns are so that gravity can also keep you in motion. So remember inclined planes? Remember inclined planes? You guys all hate inclined planes a lot? Well, a banked curve or a banked turn is an inclined plane the whole way. So when a car travels on a circular path on the road outside, it does this. But NASCAR races, it's like this. And the car travels along the banked turn the entire way. It's like an inclined plane. There's the ground, there's the inclined plane. The car doesn't want to slide up the plane to go off the race, so it is able to keep it toward the center because gravity is pulling it down the inclined plane. If you take AP Physics next year, or if you take a college level physics course, I guarantee you will do inclined planes with banked curves. Okay, it's a little bit complicated, so I didn't go into it when we did that already, but we could really do it if we wanted this chapter. But I'm going to stay away from that because inclined planes are a little bit difficult, I think, for us. So the force of friction mainly, but gravity also helps it. How about a roller coaster in a loop-the-loop? How does it actually stay? Why doesn't it just fly off the track?
The wheels.
Okay, the wheels. Give me more.
How fast it's going.
Velocity and force of gravity.
Kind of. Let's draw a loop-the-loop real quick. All right?
The normal force? And then
So it starts up here, right? It's traveling down the track. It's traveling down the track. Okay? It really wants to continue off the track this way. Right? If there was no track there, it would shoot right off that ramp, right? Imagine this was a ramp. Okay, it would go like this, and it would be launched off. But the track is here, and the track pushes it back. What is physically pushing you back, though? What force is that? What's a reaction force when I push on something? What's pushing back? Table or Paul, Cat, I heard one of you guys say it. I don't know who said it. The normal force is actually doing it here. Yeah, you were guessing a bunch of forces. I wasn't going to give you credit. You ran off like 3 or 4 in a row.
no, I said the normal force and gravity together.
Well, gravity also helps. Yeah, that's a good one.
What
So
I said.
at the top, though, is only gravity. So let's think about this for a second. Right here, here's the cart. Okay, it wants to move off that way, so the normal force pushes back, and gravity pulls it down. So gravity doesn't really help it there. But when it's at the top of a loop-the-loop, right up here, it wants to continue. It wants to move away from the circle. It wants to be a center fleeing. But the normal force pushes back. And so does gravity. Gravity also pulls down. So at the top of the path of a circular motion object, gravity and the normal force provide the centripetal force acting on the object. How about a stunt devil? How about a stunt devil? Airplane, stunt devil. Think of what are the blue devils or blue angels or something? What are they called? Blue angels? How do they stay in some sort of circular motion when they do these like little loops in the sky? What is it? Okay, so definitely friction. So the drag force on the object. What's the force that helps a plane take off? What is that called? Anybody know? Instead of takeoff, there's another word. So what's the force? The force of? Lift. Lift force, it's called. So, if a plane, right, we're going to study fluid mechanics in the year. If a plane's airfoils, aka wings, change to a certain angle, we'll have enough lift force to provide them to lift off the ground. But if the drag force on the plane is more than the lift force on the plane, it will not lift off. So what keeps a stunt devil in that circular motion are the lift and drag forces. And they kind of act together or against each other. Drag wants to slow it down. Give me like another 30 seconds, please. I want to do one more thing.
Is that why like things don't do
No, it's usually other conditions, really. There's a lot of other conditions that apply, but that shouldn't affect that. I mean, it will, but not significantly. An electron in orbit. Electron in orbit. It's not gravity. In chemistry, you talked about something called the electrostatic force. Remember how an electron moving around a positively charged nucleus stays in orbit? Because there's an electrostatic force. What about a satellite in orbit? Gravity is what keeps that in orbit. The gravity from the Earth pulls that satellite in orbit. So one last thing for the day. Okay, one last thing. And I could have done this at the beginning to make you wonder about it.
Put the lotion in the basket.
No lotion in the basket. I know you have a game. I'm getting there. Hold on. I know you have a game. So, it's not going to. So, anybody at the beach ever take a bucket of water? Right? You do this, you always wonder what's happening. Well, now you know what's happening. Ready? As you spin this, the the water wants to flee from the center. But the bottom of the cup is going to push back.
We're in the
So you can
slide
literally, no, nothing's going to spill. Okay, so the glass of water just continues to move. No water's supposed to, it's almost filled to the top. It's going to keep filled. And again, what's happening in this case, right, in this specific instance, it's going to break soon. This has been pulling all day. I'm waiting for it to break. So, what's happening is this. The cord is pulling it toward the center, and then the water wants to push out, but the bottom of the cup is pushing back with a normal force. So for this example, you have a combination of tension and normal force that are keeping the water from flying off into space or somewhere. Okay? Extra credit? Extra credit, listen. If you want to, it's up to you, find something moving in circular motion. Let me map this, obviously. In circular motion, record it, and discuss what's providing the centrifugal force. Find something that's moving in circular motion. What is keeping it in circular motion? What force is acting on it to keep it in circular motion? By Wednesday, if you want extra credit. Okay, by Wednesday. Feel free to start some of this homework. We didn't get to everything, but you can definitely start the homework if you'd like to over the weekend. Find something that moves in circular motion. Okay, discuss, you guys, what we mean. And discuss what is keeping in circular motion, what force. Okay, but you did all those. We're not something at home with us.
I don't know.
Sure. As long as you extend it, that's fine. One word, one talking. You too, Hannah. So, in this example, imagine that, and the other class didn't seem to understand what I meant by project adventure. In like middle school, did you ever do a thing where you had like a group of 10 people and you had to somehow get across like the gym floor from one mat to another? Sometimes they had like little like rolly dolly things, other ones would have ropes. Sometimes you would have like, you'd have to make like a human chain to walk across, like it was supposed to be like fire. So imagine you're in project adventure class and there's 2 islands. Okay? And you have to swing from one rope, or on a rope rather, from one island to the other. So your path would look like this, right? You would end up over here, and you would jump off onto this island. Okay, so you're starting on the left island, and you're following this path the whole way, and ending up over there. Now, if your mass is 60 kilograms, and the length of the rope is 8 meters, and if the rope itself can withstand a force of 750 newtons before it snaps, then what's the maximum speed with which you can swing? So the question becomes, how fast can you swing so that the rope doesn't actually snap? And realistically, you would solve for someone's mass. You would say, how heavy can the person be before the rope snaps? But in this problem, mass is in several locations, and it gets really messy. So I chose to say, let's say, what speed can we swing with? The mass is fixed. All right, so let's say it's a certain person, it's you, and your mass is 60 kilograms. It's like 140 pounds. 150, 140, whatever it is. So in this kind of a problem, what we want to think about is physically what's happening. And if I look and I think about a person, and I'm going to draw this pendulum over here. So here's the person right there. All right, hanging on the end of the pendulum. And at this given point in time, the person has gravity pulling down and tension in the rope pulling this way. That would be my free body diagram if I think about it. And think about it logically. Hanging from a rope. When you're hanging from a rope, weight is pulling you down. You're hanging, so there's no normal force. You're not on the ground. You're like hanging above the ground. That's an example. And then the rope is pulling back. Okay? The rope is pulling back. So we're looking at an example like this. Maybe this is the ceiling right here. Okay? As the person swings from one island to the other, if we freeze frame it right here, okay, their weight is acting down and tension is pulling up toward the center of the circle. Recall from last class that the centrifugal force always acts toward the center of the circle. Well, this is the center of the circle. The way I know that is if I were to swing this around, right? The center of the circle is exactly where this pen case is right here. That's the actual center. Now we're only looking at some sort of cyclical motion with the pendulum, just back and forth, back and forth. But this really is a circle, because if I do that, I can see that it's a full circle. So I'm looking at an arc length of the circle. This is definitely circular motion. Now, at this point in time, tension is acting toward the center, and the weight is pulling down. Now, if I continue through the path at the bottom, how would my free body diagram look? If it was at the bottom like this now. So now I've got, again, imagine now you're at this stage along the way. What would my vectors look like now? What would my force vectors, those arrows, where would they be directed? How would I draw them?
FG would be down, FT would be like FN.
Yeah, FT would be good, like FN, straight up. That's what it would look like in that case. So what we notice is that as the pendulum swings back and forth, FG still acts down, but it's always going to be acting at a weird angle compared to FT, except when it's right down the middle. When we pause it right here, gravity and tension act opposite each other, right? But at any other given point in time, it's at some sort of an angle. You see this angle right here I'm talking about? FG is straight down in the beginning, but FT is acting diagonally. So what happens is, and this is something that it might be useful for you to know, the maximum amount of stress on a rope in this situation will be at the bottom. So we're going to analyze this scenario at the very bottom. All right? Again, and think about it logically. Tension is pulling up on the rope. Gravity is pulling down on the rope or down on the person. That will cause the most stress in this rope when it's like this. At any other instant, there's very little stress on the rope. Right here, the weight is pulling down, but there's not much stress on the rope right there. And the stress increases, and then increases, then increases, then increases. But as it goes up, the stress decreases, and the stress increases, and the stress decreases. So the rope is feeling this fluctuating variable stress on it. So the stress changes as a function of the angle. Well, the angle, that's 90 degrees right here, so this angle of 90 degrees between the rope and the ceiling, this would be the maximum stress. So we're going to look at this scenario when the person is at the very bottom. Okay, that's how we're going to analyze this. So just to give you a little quick synopsis before we come up with the equations. All right, so for free body diagram, where to be here, it would look like this. Remember, FT up and FG down. Okay, again, we're analyzing when? We're analyzing when the object is at the bottom of the path. Now, think back and recall Newton's laws. Newton's laws tell me F equals ma. And this F on the left-hand side is really the sum of the forces. Okay, remember that this is really the sum of the forces equals ma. At the bottom of the path, what forces are acting, and how could you label them? At the bottom of the path. When this object is here, what can I replace the sum of F with? What can I put in place of this based on this diagram? And think of toward the center of the circle as positive and away from the circle as negative. FT minus FG. Tension is pulling toward the center. Gravity is pulling down, or acting in opposite directions. Whenever there's circular motion, think of toward the center as positive. Remember, the centripetal force, this is really centripetal force here, is Ft minus Fg. How do I know that? Well, really, look, this is what's happening. And I kind of skipped this step. Okay, but there's a little step that might go right in here that says, well, Fc is equal to m times AC. So, if I recall, Fc is made up of some force depending on the scenario. Remember, when you're revolving something on a rope, it's tension. When the moon is revolving around the Earth, it's gravity. When an electron is revolving around the orbit of, or around the nucleus, the nucleus, it is the electrostatic force. What was the other one? When a car is going around a racetrack, it's friction that's keeping it in line. Well, here, tension in the rope and gravity are the two things that are acting on this object at the instant in time. And they act in opposite directions. Now, this A right here is really the centripetal acceleration, because this problem is moving with circular motion. What is the formula I should plug in for AC? What was the formula for AC, Kev?
Isn't it VT squared over R?
It is. VT squared over R. And I've got on this side still Ft minus Fg. Okay, Ft minus Fg. So, in this problem, we need to consider the fact that this is very different from what we're going to do in today's lab. Right now, and I'll try to give you different perspectives on this stuff so you can understand many applications, not just one. So right now, yeah, there's tension on the rope, but gravity's acting against tension. That's why this gravity is included, right? Now, if I were to spin this way, though, okay, and I were to keep it in circular motion horizontally, so this is moving only in the horizontal plane right now, imagine. Tension is still pulling this object toward the center to keep it moving like this. But which way is gravity acting? It's still down, but it's not acting with tension anymore. Think about it. Tension would be acting this way. If I freeze frame this right here, right? Pause right here at this point. Tension is pulling in your direction, to your left, correct? Because it wants to go this way, but tension is pulling back this way. So when I'm spinning this, and I pause it right here, tension is pulling this way. Gravity is pulling down. So gravity is acting in the y direction in the case where we're going to look in the lab. So gravity acts down, but tension itself acts toward the center. So it's going to be a little bit different when we do the lab. But for this scenario, gravity does affect it, because tension is pulling up and gravity is pulling down. Those act against each other. So this gravity takes an effect in this problem. So if we were to solve this and try to figure out what's going on, we can think about what's given, but we also have to think and recall, what is the weight of an object, really? What formula can I replace Fg with? Mg. I heard a few people say Mg. Good. Recall that Fg is always equal to Mg. Now, there's a common mistake that some people will try to do here. What's the mistake? What's the mistake? Again, it's not correct, but what is the mistake? Yeah, why can't you cancel the m's, Victoria? Correct. Correct. Right here. You're missing an m here. If there was an m in all terms, you could technically factor out the m and then cancel m's on both sides. You cannot cancel m at this point in time. Our goal is to figure out the velocity, or the maximum velocity with which a person can swing. So our goal is to find Vt. How do I get rid of the m and the r? Jake?
Well, to get rid of the n, you can divide by n.
Good. And get rid of the r, you can?
Multiply by r.
Correct. So I could do this. I could technically divide by m by doing that, and multiply by r by doing that. So technically, if you think about this, this is like a coefficient right here. When you have a coefficient in math, how do you get rid of it? You multiply by the reciprocal of that fraction. Well, what's the reciprocal of m over r? It's r over m. r's cancel, m's cancel. Okay, see how your math skills are constantly improving now? So you have a fractional coefficient, such as this one, m over r, that's really a fraction, multiplied by r over m on both sides. How do I get rid of the square that's left behind? Square root it. All right? So that's what the velocity would be in this case. Algebraically, not numerically. Okay? And think about this for a second. If the velocity is any bigger than this, what's going to happen to the rope? It's going to snap. It's going to break. Very good. Because the allowable tension force in this problem is given to you right there. If this number increases, well, this is constant. The length of the rope is constant. This is constant. This is constant. So if Vt were to go up, what would happen is Ft would go up. The rope would feel too much force, and it would exceed the allowable tension in the rope, and the rope would snap. So our goal here is to find Vt, and that's going to be a maximum value. The answer we get is really a max value. So plugging in numbers here. The length of the rope was given as 8 meters. That's the radius of the circle in this problem. The mass of the person was given as 60 kilograms. Do you see why now, by the way, I didn't have you solve for mass? Mass is here and mass is here. Okay, so I made this problem a little bit easier by solving for V. The maximum tension that this rope can withstand is 750 newtons. Please remember that you need to multiply 60 times 9.81 first, and then you can subtract it from 750. in the other class, some students made the mistake of subtracting 60 from 750 and then trying to multiply that by 981. But PEMDAS tells us multiplication comes first, so simplify this right here and then subtract these two quantities. Please check. Take out your calculator. Please check. Check it. What is it? What do we got? Very good, very good.
Okay, nerd.
I see divided by 8 over 60, that's Yeah, calculator knows that the division first. I would put parentheses around a fraction all the time. Depends on where it occurs in the problem, it won't work anyway. So, this is the maximum allowable velocity with which the person can swing. So if this is the maximum allowable velocity, technically, what should my answer kind of say? Because numbers could be smaller than this, right? Think about it. If you swing with a velocity less than this, it's still okay for the rope. It's if you exceed this velocity that it's a problem. So how would you answer a question where there's a range of possible values? Instead of an equal sign, what kind of sign do you use instead, Jake?
Less than or equal to?
Yeah, very good. So VT is technically less than or equal to 4.6. And this is where you have to make sense of the problem being asked. So in our problem it said, determine the maximum speed. So yeah, the answer is definitely 4.6. But if the problem said, determine the possible speeds that the object can take on, this would be a range of possibilities. Anything less than 4.6. But because ours said, find the actual maximum, we answer with just 4.6.
The radius be 8 wouldn't the radius be 4 if the length is 8?
No, because remember the rope is like this. This is how it's swinging, right? Isn't this the center of the circle? So this, my arm, is the length of the rope. It's 8. Yeah, if it was like through the ceiling and connected somewhere else and it was doing this, then it would. Because that'd be the diameter that we'd have. Okay? Any questions on this one? Do you get the idea? Right? That centripetal force is provided by something, and then that is equal to mv squared over r. Okay? mv squared over r. So what I want to do now is to give you a little preview of the lab before you even start it, before you even load anything. So don't load, actually I didn't even put the lab on Moodle for that reason yet. I have to put it up there in a second. So what I want to do now is demonstrate with you an example of this. And I had a nice one here earlier. Where did it go? Here it is. All right. So what I'm going to do is I'm going to load the lab. You're not going to load it. You're just going to watch. It's not even on Moodle yet.